Hi, my name is Dennis. Welcome to Foundations Networking, Device and OSI Concepts. Let's look at what we'll be learning today. In our learning objectives, we're going to identify what the OSI model is, the components and the network devices, and examples of each layer. OSI stands for Open Systems Interconnect, and we'll look at how it's the backbone for today's modern networking. Also, we'll understand how packets are forwarded across networks and how encapsulation and de-encapsulation works across these concepts on how we send and transmit data today. Now, first off, OSI concepts, we have a 7-layer model. And what that really means is that it was a framework to really consolidate what the standards were previously before networking became mature. Let's look closer at it. So the OSI model, also known as the Open Systems Interconnect model, has 7 different layers. Let's look at each one of them as a whole. So as you can see here, we start with the top-down approach. The transmission of data starts at layer 7. We also have presentation at layer 6, onwards through layer 1. Each of these are separate isolation segments that turn data into actual packets that go across the network via devices that you commonly know today. Network switches, routers, firewalls. These are all examples of different devices and technologies that operate on the entire OSI model stack. The whole point of this was decoupling and modularity. The whole point of great architecture is to make sure you decouple and modulate everything possible, whether you're in the cloud or on the networking side. We have these different layers to make sure we have distinct, clear definitions on which each portion, protocols, and technologies need to do with each other. As mentioned earlier, we also have inter-vendor compatibility. So back in the late 70s, we had issues with different vendors having different concepts of what networking meant to them. Over time, the OSI model was created so that different vendors could have focus on different layers of the network and so that they could actually do what's best for their protocols, their stacks, and their technologies at the time. It was an early standard setting attempt, and that's why we have it today. So remember, we'll touch into encapsulation and de-encapsulation in a moment, but let's look at each layer and determine what happens with each layer for the application that you're using. Remember that when you're transmitting data, you're always starting from the application going downwards. The receiver is receiving your signal and receiving it back up the layers in a U-like format. So remember, we're going down and then back up as we transmit and receive data together. Now, the layer 7 application layer is also exactly what it sounds like. It's the applications and applications that utilize everything. So examples include DNS, HTTP, which is Hypertext Transfer Protocol, SSL, and many other different items that you've seen over the course of your utilization of the internet. Think of anything application layer is whatever the data means to the application. It doesn't mean anything to the networking portion of the rest of the stack. It doesn't mean anything to other layers. Only the application understands what is going on. In this case, if you go to a website, it understands HTML, the data that is related to HTML, over protocols, which are really rules and standards of transmitting data to and from the different networking devices. These layer 7 protocols are specific to the application itself. And the next layer down is the presentation layer. At this layer, we are encoding. We're focused on encoding our data or our payload. So I'm speaking to you in US English or American English. That is a form of an encoding of language, natural language. If you spoke a different language, that's a different version of encoding. If you speak computers and you want to present that computer to a colorful display, right? You might have drivers and many other protocols or helpers. So whenever you think of presentation, think of how data is presented to the receiver, how it needs to be formulated. Other examples include compression, encryption, and then there's other encodings that computers speak about all the time. Base64, ASCII, which is the American standard of coding here, and then the universal transformation field of 16 bits for all these codified versions of how we represent characters today. In fact, if you're looking at emojicons, or if you look at foreign characters, UTF-16 is today's latest standard. Again, presentation layer, think encryption, compression, or just translation. Anything that we do to transform the data into a way that the receiver represents and can understand what we're saying. At layer 5, this is where it gets a little tricky for a lot of new people. And let me explain a little bit further. Layer 5 is about session. So if I was sending you a package, I'm creating a package that has payload, my data, layer 7 application data. I've made that instruction manual for the package in the language that you need to understand how to utilize that payload or that gift I'm going to send you. And at the session layer, this is where I actually send you communication about how I'm going to send it. How are we going to set up the communication and the routes? How am I going to send you the package as a whole? That's what the session layer is all about. Now, some applications actually utilize layers 5, 6, and 7 together. Some applications do not. So the less integrated your application is, the more you'll need to rely on layer 5 protocols. Now, examples including SIP, which is session initialization over IP, which is related to voice over IP today. So if you've never used a telephone that isn't connected to a network by any means, uses some sort of adapter, you're using an analog telephone, but over modern day we use SIP. So voice over IP, SIP is the way to create that session to determine if there's a call being made. We also have SIFs and SMB, which is server message block. They are together as complementary protocols. Windows, Linux, and many other operating systems use these to transfer files, to set that session, to understand between different operating systems, different computers, what data is going to be sent and how. Finally, at layer 4, we have transport. Think of transport as ports. So whenever you think of layer 4, think of ports. So you've probably seen this if you're a gamer or if you've been doing networking or firewalling at any point of your career. We have ports 0 to 65, 535 as a possibility. Again, these are 16-bit protocol-based ports. So you have a maximum of 65,000 and some change. Examples include TCP or UDP. Think of these as garage door ports, right? When we think about ports, think about open garage door spaces. For those of you who have houses, you might have a garage that can hold 3 cars, ports 1, 2, and 3. And so you'll send data, right? You'll send data specifically to that port on the receiving end. Now, that's not your host. That's just the garage of a particular port, such as a house. So when you think of transport, think of all the different ways that we do splitting the data into different aspects or chunks, hence segmentation here if necessary. However, we're focused again on transport. From what garage to what garage is it going to? So for instance, let's clear the screen real quick. So if I have point of origin A and I have point of origin B, I can still have, this could be garage port 3, 4, and 5, but I can also send it to garage ports 1, 2, and 3. And so if my package needs to go from port 5 internally to port 1 on the receiver end, that's what we mean by virtual circuit. That's what we mean by transport. We're transporting the data from one port to the other. Now, next we have networking. Networking is based on routers. Think of routers, think of IP addresses, think of anything that are based on addresses. So, just like you have a specific port for your garage, you need to have inside your garage, you have maybe a house, right? You have a house, you have an address, you have 123 Main Street, for instance, right? And you might be at a specific city and state. And of course, your zip code if you're in the US. That is the way we address where packets are routed to and from the internet and among ourselves between networks. So for you, instance, you might have a router, you might have multiple networks. So for those of you who might have had multiple networks on your own home machine and you had trouble accessing the next host or port over, you might have not had the correct IP addresses. So at the end of the day, think of layer 3 networking as IP addresses from one address to the other. The layer above it is the ports of where it goes, very specifically which garage door it needs to go to. So if you have Amazon Prime, for instance, and they open up a specific garage door based on your app, that's your layer 4 version of the port. Them getting to your address, to your house from their distribution center to yours, that's an IP, right? That's a port and IP combination. Layer 3 would be your address. Layer 4 would be your ports. So think of that analogy as you're thinking about that. And at this point, we're not about data anymore or segmentation. We're about packets, right? So if you had to actually take my one package and divvy it up into different pieces or components, and let's say I wanted to transport that over different routes. I want truck 1, truck 2, and truck 3, and truck 4 to all take different routes, the most efficient routes possible to get to my house, and I can reassemble the gift, or you can reassemble the gift that I just sent on the packet layer. And that, think of packets, IP addresses, routers; those are all layer 3 items. And this will make more sense in a moment when we get to our lab or our break section. We also have layer 2, which is data link. We're taking finally the IP addresses, the packets that are encapsulated with everything together. So when you think about encapsulation, and we go down from layer 7, we'll say layer 7 to layer 1, we're actually saying we're starting off with our data, which is data right here. That's horrible, but it says data. And then we're actually adding on to each one. So when you create a package, right, I added my gift, my payload to you. I need to add certain features, and those are what we call headers. And we encapsulate the package into another package somehow. So now I added information about perhaps my ports, right? That's layer 4. And then we added information about my address. So instead of my garage, we also add my address. And so instead of slapping a shipping label on it each and every time, you're actually putting it into another box and another box and another box each time, encapsulating my original data together, eventually until we get to what's called a layer 2. Now, layer 2 itself, when we're encapsulating all that, it simply just means that we're now on your local network. So if I sent you a very specific package to your home address, right? Your garage is your ports, your address is your IP address equivalent, and then when you bring it inside to your house, maybe, or if your office, maybe you have a specific room. Maybe you're Bobby, or maybe you're Linda, and you have multiple people living in your house. Where does it go internally? The data link layer actually takes those packets and transforms them into what's called frames. Right? Those packets become frames, and what happens is everything is stripped off. There's the raw data, and it's re-encapsulated inside a frame to say, hey, I need to deliver Joey's package to Joey in his room. Specifically, that's where his address is. His room might be on floor 2, room 3 of a particular house. And that's what we say by data linking. We're linking the data back to the original construct of the owner, closer to the foundations here. So we get closer to your recipient or your host as you get the data back in. Now, when you think data link in layer 2, you should think of MAC addresses. These are 48-bit addresses known in hex. So you can think of them as octets. Similar to IP addresses, those are octets too, but think of 00, 00, 00, and 00. 8, 16, 32, 48, right? So at the end of the day, MAC addresses are another version of an address, but think local. Think rooms. Think your building, your cubicle, whatever it may be. That's what we say by switching the frames, right? Switches, network switches. We're switching from packets to frames. So that's when you can help yourself think about what layer the switches fall under. And also we have the concept of VLANs that we'll go over later on in the labs that you'll learn later today. So think of packets turning into localized mail carrier groups that are inside your local building or your local house. Finally, we're at layer 1, the physical layer. The physical layer is the simplest one to understand. You've probably utilized them your entire life as you've used the internet just like you use today. Think of modems, fiber optics, coaxial cable, Wi-Fi standards, or even standard network jack plugs, such as plugging in copper twisted pair. Some of you might see this as Cat5 or Cat6 when you buy a network cable online. And those are just ones and zeros on or off. Right? That's just sending a stream, repeating the stream if necessary, from one destination to the other. No smartness, no switching, no understanding of a route, no forwarding. It just goes from one end to the other. It has no understanding of what data means. It just knows that it needs to send zeros and ones across the medium that you select. That's it. Now, that was a lot to really, lack of a better term, encapsulate. But encapsulation, as we summarize all this, we talked about the OSI model layer, how there's different requirements. But as I sent you that package, if you think back to our analogy, I'm sending you data, right? And your data over the network is the equivalent of me sending a package to you as a gift, a toy perhaps, whatever it may be. We add the application layer information, right, at the data layer. You might have other application-specific items, and notice that we're still dealing with the data. L5 to L7, we're still dealing with data, right? We're understanding that we need to talk about a shipping invoice. So where does the shipping invoice come from? Or what do we talk about shipping invoice? That might be the phone call I make to you saying, hey, Bob, I'm sending you a package. Here's how it's going to come through, how many packets it should be, how large, what's my dimensions, how heavy it's going to be, what you'll need to actually process that package or open it when you receive it. That is L5. L6 and L7, when they add that headers and encapsulate accordingly from the user data as we go down the stack. Remember, that's just including instructions or transforming the package or the payload specifically in a way that you'll understand what I'm sending to you. So if you have requirement that you need different instructions, such as a different language, to how to assemble my gift to you together, that would be layer 6. And of course, layer 7 is originally the original payload, my original gift to you. Now with that out of the picture, we need to focus on layer 4 through layer 3. Layer 4 and layer 3 are together. Remember, layer 4 is at ports, my garages. If I'm sitting from my garage 1 and someone's picking it up and it's coming to your garage number 3, port 3, let's say you have garage 3, 3-car garage, that is our virtual circuit. But to know that where garage 1 and 3 makes sense, right? There could be everyone that has 3 garages or 2 garage ports, and what port do I send it on? So layer 3 has the IP addresses. And in today's time, we use IPv4. And so what's an IPv4 address? Well, it might look something like this. So if I take an IP address and port pair, right, I might have something that looks like 11223344, and then my colon right there is my delineator that I have a port. And I might have port 80 right here, which is a standard clear text web server in most cases. Now, I have a full address of where it needs to go to and what garage door it needs to hit. That's where I'm sending and routing information to. Again, that's at the packet layer. Now, once it gets inside your house, it needs to go to your room. Let's say someone's bringing that to you, or you're in an office and someone's bringing that to you. What room are you going to? Well, you might have Bobby has a very unique room. And it's a certain offset and a certain area of the house. And that's where you think of MAC addresses. Again, MAC addresses, which means media access control addresses, which are, again, 48 bits. Now, interestingly enough, if I say this together, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, again, 48 bits. If I cut it in half, the first 3 octets of that 48-bit address range, that's an OUI. And that simply means you can actually determine it based on the typical vendor. So although you can spoof addresses, by default, everything's burnt into your actual addresses. So if you have a network card, if you have anything that uses the network, a device, Internet of Things, you actually have a 48-bit MAC address coming from the vendor. The first 3 octets are within a very specific vendor range, and that can help us determine what's on your network from a vendor perspective, right? What kind of room you're in, or something like that. The last 3 are really unique to the device itself. So that's how you can actually route your remainder of your package locally, right? Local to your network, locally inside your house, to you, Bobby, and then eventually at layer 1 you receive it. Maybe you're finally handing it off by hand, and you're finally opening it up, interpreting it, and then at layer 7, your application, which is your brain, I guess, would actually interpret and do what you need to do. So to summarize everything else together, I know that was quite a bit. Again, your labs will help you clarify this, as well as our demo. Encapsulation basically means you're taking something, you're adding in headers, and you're putting it into boxes and boxes and boxes of stuff. So rather than sending a package and adding labels as necessary, you're actually putting it into a new box and another box and another box that has the greater information. Because remember, each of these layers, they don't know about each other. All they do is strip off one layer and say, oh, that's my header, I'm that layer, I need to do what I need to do with that, make that decision, send it all up. And that's what happens. So think of it as a multi-routing mail carrier with different teams together that don't know anything about each other, and they only know one thing about their specific zone. Similarly enough, encapsulation also includes de-encapsulation. So if you're sending a packet, you're adding in headers going down the stack. If you're receiving a packet or any kind of data, you're actually going up the stack. So whenever you're going up the stack, remember, back up here, back up from layer 1, back up to layer 7, and that's what's happening. So that's still part of encapsulation, but you're actually de-encapsulating as you're receiving. Something very important to keep in mind. Now let's take a quick break, and then we'll get right to our demo. We'll see you then. All right, welcome back. Hope you had a great break. Let's move on to understanding visually what it means by encapsulation. So I have my Windows host up here, and I want to show you a few things. Just like with Linux, and just like with Windows, you can use Wireshark. You can also use your terminal command prompt. In this case, I'm using PowerShell. If you're following along, the same commands still apply in Linux, so be sure to do those with us in the lab. Open up your terminal, spin up your VM at this point, and let's get cracking on learning. So when we're talking about signals, right, signals mean a lot of different things. As if we go into the device manager, and the reason why I'm using Windows is because it's easier to find devices, right? That's my hardware. That's my hardware that includes network devices, including my network interface cards that we talked about in previous modules. Again, these are all network interface adapters using specialized drivers that communicate from my OS using my user LAN to my kernel space, so we can interact accordingly with that. Notice that I have multiple network cards in here, including my Bluetooth, my local network card here for wired connections. I also have my wireless one using Wi-Fi 6 and many other ones. And some of these you'll see here if you're a Windows user in our class, you'll see VirtualBox or VMware making adapters so you can have your VM communicate with the internet. Now, those are examples of layer 1 devices because they're taking in signals of ones and zeros. Now, when we start sniffing traffic on our computers, we're actually doing a couple of things. We might do it for troubleshooting, we might do it for forensic needs, whatever it makes sense to do. So, I've opened up Wireshark. You can do the same thing inside your Linux OS. I'm just showing you the Windows. All of our commands that we'll show you today is the equivalent to Linux. Just try it out. And if there's a difference between them, I'll also note them as we go through this. So to further talk about encapsulation, we should really show what a packet looks like. So as you can see here, I can actually determine what my different network interface cards should be capturing on. So I'm going to select Ethernet 2 because that has stuff. I'm actually going to set a filter, and you'll see this in your lab as well. I'm going to set a filter to specifically the host I want to speak to, hence a layer 3 IP address. So I'm going to say host 8888, which is a Google DNS IP address. If you don't know what that is, feel free to Google that actually. And you'll see the address and what it's for. I'm going to say that's my capture filter, and now I am inside waiting for packets to happen. Now, I can still go to the internet. I can still ping 1111, which is an Amazon as Cloudflare own. Notice that it doesn't show up here, even though there's network traffic connection, because I've set my filter accordingly. It's called a capture filter. Now, if I click clear here, I'm also going to do ping 3 times 8888. Oops. And for those of you who are running Linux, you won't have to do that. But unfortunately, with Windows, I have to use what's called privilege escalation, which is elevate my rights as an admin, kind of like sudo with Linux. I have to create a new PowerShell prompt accordingly. With this, I'll just say ping C3, which is count of 3, 8888. And I'll try that again. Oh, that's right. Also to note that if you're using Windows, ping C will not work. You'll have to use ping N. To understand what your syntax look like, you'll use ping /, enter, and that's the version of equivalent of tac help or tac h for your Linux-based distributions. Notice here that we use -n, that's lowercase n for ping as opposed to a -c. So I'll clear the screen. And I'll do ping -n. Remember that in Linux, this is -c, 3, and we'll say 8888 as my host. Enter. Now we should see items here. Very interesting looking items here. Pinged it 3 times. And notice, but we have 6 packets here. 6 packets. And the reason why we call them packets is because it actually traverses the internet. It left my local network and traversed the internet. Why? Why is that considered so? Well, we have the magic of encapsulation right here. In Wireshark, and I'm going to stop the packet capture right now by pressing the square here. In my packet capture, I'm actually seeing interesting stuff here. Here's the layers going on. We have a single connection in and responding, but here's what we have. We have our frame being built, which I said we had our 48-bit MAC address space. And notice here, it's detecting my vendor as BizLink or whatever that may be, followed by my 3 remaining octets, which are unique to my MAC address. And again, the destination MAC address, this will actually be, how would you know what the destination MAC address is? Well, you actually don't. Your router actually is the destination because you're leaving your network. And so if your router, if you want to find what your router was, in Linux, you're using IP space A or IP space ADDR. In Windows, we use ipconfig, right? And if you're using a Mac and older versions of Linux, you can also use ifconfig, ifconfig. Now, notice that I have a default gateway not listed here. And unfortunately, that means that's just for the VMware portion if I have my virtual machine up. Here's my adapter because I just captured on Ethernet 2, and I'm sending it out, and I am using an IPv6 dual stack with IPv4. Here's my IP address, which is at layer 3, and here is my gateway. That's your router. So usually when you see a .1, you actually think of your router. Your router is actually something like your firewall or something of that nature. So I'm going to open up my browser and show you that I'm actually using a very particular vendor called Ubiquiti. Now you can use any firewall you want. It could be your cable modem router that comes with it, Netgear, Linksys, whatever it may be. But it might look something like this. Your router might be your device in your house. You'll log in, and it actually acts as a router/firewall for you on your behalf. So all in one. Now, what happens is your modem creates the ones and zeros being sent out and reproduces it by sending it from your network address card to your switch, which is sending those ones and zeros at the hardware layer, which turns it into a frame. So notice that we go from ones and zeros of my data bits, where it doesn't understand anything, just coming out of the interface. But now at layer 2, we got MAC addresses, and this is the destination MAC address. Is actually the destination MAC address of your default gateway, hence your router right here. The inside IP address of your border edge of your network. So if we had to draw something like this, we'll just draw it really quickly here in Paint, just to give you that concept here. So if we have, let's take our modem, actually let's take our host, we'll take a network switch, we'll take our router, we'll use a circle for a router, how about that? That makes it a little bit easier to distinguish it. And we'll take our modem, and then whatever over here, right? We have the cloud or the rest of the internet. So we'll use the term internet here, internet, and then we'll just increase our size here so you can actually see this. And we'll make it blue, nice and big here. Internet. All right. So as we go through, we actually have this via connected via hardwire or via wireless, whatever makes the most sense. In between these, we have what's called, we have your host, which is your computer, host 1. Right? That could be your computer, that could be your iPad, that could be your whatever you're using to access things on the network or the internet. You also have your network switch. As we remember from our OSI model, that is layer 2. We also have our router / firewall, which is, in my case, you saw Ubiquiti and some sort of white slender device. And then we also have our modem. Now our modem, remember, is going to take the signals, receives data, and converts it, modulate and demodulate, and convert it from that into ones and zeros to actually connect to the rest of that. So if you're using cable, for instance, right, The ones and zeros will go over your cable line. The modem will actually take your digital bits and bytes and turn it into analog processing, hence modular, demodular, hence modem. That's where the term comes from. As we're sending our data, between our hosts, we're pinging and we're creating the data, and there's MAC addresses, and the MAC address needs to say, hey, it's not inside my local network, which is 192.168.20.0s in my case. So if I go to ipconfig again, notice that up here, exactly what I said, 192.168.20.198. I'm going to 8888, right? Quad 8s. And so it's not inside my network. Hence my router and my firewall are also on the 20 dot something. So what happens is it actually goes, oh, I'm not a frame anymore. It's not local. So I'm going to encapsulate it one more time, create a packet at layer 3, move it through my firewall / router, and eventually it gets translated into the ones and zeros of signals from your cable modem or whatever you're using. That's what's happening here in this ping request going on. So we're having actual data. Why encapsulation still applies? Well, let's take a look at what that encapsulation really means. Let me resize this real quick. Notice I have something interesting right here. I have the ABC through G, and then I have high at the very end. That's what Windows sent. It'll be a little bit different for Linux, but essentially I'll have a string of different characters. That's my data. That's my payload. It's being encapsulated inside a signal, inside a frame. Hence, think of frames at layer 2, MAC addresses. And then eventually it gets encapsulated into a IP address at layer 3, and it goes, hey, I know my source and destination home address, but something interesting happened here. Now, I don't see a port. Do you see a port? No, I don't. And this is actually because ping is at a layer 3 protocol. And why do we have layer 3 and know we have data? We have to send it somewhere. Well, what happens is the router actually understands this payload, or actually won't understand it. It actually will receive the message and send an encoding back. So ICMP is type 8 ping request, and that we might receive a reply, which is right here, which gives us a reply type 0, code 0. And that really means that this is all happening at layer 3, but there's no ports. No ports whatsoever. So you can still send data over layer 3, but nothing else above the ports will understand. So your OS won't understand this data. Now, the reason why Wireshark can see this data is because it understands all layers from layer 3 onward, layer 2 onward, sorry. And so you'll have this in here, and really, the routers and your firewalls are not going to know what to do with this at layer 4, right? It only understands that it received some sort of packet at layer 3, and we got a response. So ping is actually a good way to understand if the host is alive on the other end. If the host is alive, not necessarily the port or the garage being open. To understand this, we'll go one level further, and we'll use our famous ncat command. We'll use ncat. I'll use -nv for non-resolution and very verbose connections. I'll say 8888 again, and because I know it's a DNS server, I'm also going to say 53, and I'm going to try to create a TCP connection. And look here, the colors change. We have so many more packets, so we have not just a bunch of replies again, we have 5 packets, actually one less than what we had earlier. Remember that each ping got a response back, so we pinged 3 times, so we actually got 6 packets back. So let's look at here. I have 20.198. Our destination is definitely 8888. And now I said my destination port. What layer is that, everyone? That's right, layer 4. And notice that I came from garage number 33,920 on the same connection. Notice that these are still the same, so the same connection to the same port on 53. Now notice that I am getting a response, but it's actually creating what's called a 3-way handshake. So it's actually creating and finishing the connection, and it's basically saying, hey, I'm ready, my connection is open, it's time for you to receive data. Now this is not data, this is just the little bits and bytes that are being interpreted as data when it's not. To send the actual data, we'll say hello. And you'll see here, oh no, I sent the word hello data here, right, at layer 7. Notice that I have a new layer right here. So we got from layer 2 to layer 3. Now we have a layer 4 with the ports. And then on at the very end here, we have the segment data at layer 7, hello. Unfortunately, Google did not understand this. Google did not understand when I was sending it because DNS protocol doesn't understand you saying the word hello to it. And so it sent me a reset request and it terminated the connection on my end. And if I want to do the same thing on mine, this red means reset, means terminate the connection. I'll press Control C, and I'll return back to the screen and notice that nothing else changed because as long as you send a reset from one side, no matter what side it is, it actually terminates the connection. So that was an example of 4 layers plus my my data, which is at layer 7. What happens when I need to go to a layer 7 protocol? What does that look like? Notice that we're encapsulating, we're adding in, we're bundling in more and more and more as you see in our screen here. Let's clear our screen and let's clear this. And then this time we're going to use a different capture. So I'm going to file and close. Continue without saving. And I'm going to continue, but I'm not going to use Google's host address anymore. I'm actually going to use TCP port 80. And there might be a lot of traffic coming in and out of TCP port 80. Depends on your network and depends on your computer. Try not to look at a lot of things at the same time, but follow along with me. I'm capturing on TCP port 80 instead, so anything going out to TCP port 82 and back. I want to go to something that I know is going to have a layer 7 protocol that my browser would understand. So with that said, I'll create it. You can use wget to do the same thing inside Windows PowerShell, which usually means invoke web expression, but wget's the alias. So wget inside Linux is an actual tool. And we'll say portquiz.net, and then there's an assumption that it's already 80. So I can say 80 right here, or not. So I'll just portquiz.net, and that automatically assumes that we're going to HTTP port 80. You can add it at the end of here, but it wouldn't make a lot of sense. So portquiz.net is what we're going to use to test. And notice, oh, now we got some more interesting details. We've got a lot more packets. So 15 altogether in this case, 1 through 15. And here we actually have a application layer right now. Our applications on our browsers didn't really understand ports and IPs. It understands data. It understands how to resolve and give you data, presenting it to you in a meaningful way. This is that data, right? This is all HTML related stuff. This is me equivalently getting, downloading the index.html, and I'm also getting the PNG files with it. Notice that the GET request is right here, which is a way of requesting information from a web server. We'll see more about that in the near future. Notice I added more layers. So we went from layer 2, 3, 4, and then layer 5 through 7, where they're kind of jumbled into one because our applications are smart enough to understand what that is. So we don't need any other helper protocol. So HTTP is the actual protocol, hence hypertext transport layer. Protocol for that layer 7. And of course, we have our get method, which every time you go to a web page, you're saying get me data. Get index.html by default, which is get / here. And what is my response? Well, that's my request. And it gave me some responses in here that make sense to me, sort of, right? But if I do a right click and follow stream here, in this case, HTTP stream, I can see right here, I'll zoom in, that we have quite a bit of data to us, right? That's what a web browser would get. Now, different things happen, and so we're just basically saying here, we got some data back. Now, that question to really ask yourself is, does that matter anything to your firewall? Does that matter anything to your modem or your network switch? Think about it. Pause the video, think about your answer, and get back. Okay, I hope you had a great time pausing there, and really, it doesn't mean anything to a layer 4 firewall. It doesn't mean anything to lower layers. All this data here, including our idea of testnet connection and whatever this is telling us in English, which is ASCII text is our encoding, right? Right here, that's our encoding. That's layer 6 already for us. It's already bundled in for us, right? We don't need helper protocols. And it also doesn't mean our routers don't care about it. It doesn't know anything to do with it. It doesn't understand HTML. What it does understand is layers 3 and layers 4 down here, and then your network switch actually understands the MAC addresses right over here. So that was a really quick, short demo. Hope you enjoyed it. We're not done yet. Let's take a small 5-minute break from here, and then let's get into understanding an overview of network devices to kind of summarize and wrap up what we'll learn in this module. We'll see you then. All right, so welcome back. I hope you had a great break. Let's get to our next portion of it, which is network devices overview. Now, we had a little bit of discussion around where routers and modems fit in conceptually. We want to solidify that knowledge with our OSI model, and what we just demonstrated today with our encapsulation. Again, encapsulating our data into packets, into frames, and then it gets de-encapsulated on the receiving side. So again, layer 1 devices, modular demodulation. Now, modems do this. Now, to get you a better understanding and appreciation for just how far we've come, digital signals are always 1 and 0s, right? 1s and 0s. So whatever can be interpreted as 1s and 0s, true or false, that's digital signal. Notice that as a square line. So when you look at analog, it goes into sine waves. That's a sine wave right there. And if you think about frequency modulation and radio or amplitude modulation, so frequency is saying I'm going to have a bunch of these, right? Amplitude means I'm going to go longer up and down with longer peaks and valleys. And so that's how you actually get more high quality digital based radio, HD radio in your car closer to the city, because there's probably more towers there to give you more frequency modulation, more ones right up here, right? Peaks and valleys of zeros, 1s and 0s. That's what that really means. So that gets interpreted by the modem, not routed, no decisions. It just gets interpreted. How far is a 1 versus a 0? How far is a 1 versus 0? And it gets interpreted back into layer 1, so you can hand it off to layer 2. So think of layer 1 devices as nothing but repeaters. Point A to point B, I interpret 1s and 0s. Layer 2 devices, just to illustrate even further, remember we talked about 48-bit MAC addresses, right? And we cut it in half, right, which is 3 on each side. First half is the OUI, which is the vendor base, so you can actually tell or guesstimate what vendors that you have on your network. And the last half are really the uniqueness. So your first half could be what floor you're on if you're looking at a single family home. The last half being what offset is your room if you have multiple people living with you. And what happens is when we talked a little bit about frames and the data is encapsulated in the frame, and you're probably thinking, what does that mean to us? So really, we're taking the addresses locally, so mom to dad, whatever we are in the house, and we're saying, hey, where is dad's room each and every time? As if, because computers aren't smart, they don't have any idea of what memory means to them. They just do what they're programmed to do. So it's like they always forget. And so when they always forget, they have to look up the table on the switch. And the switch basically says, hey, I know where mom and dad's room is. Send it to me over here. And it's going to send the data directly over there to that MAC address instead of leaving the network, right? It's never leaving your house. So MAC addresses are a way of giving you that data link, linking data on the same network segment, right? This is basically the same if you're saying, I'm on 192.168.0.0 right there. And so if I had my network like this, /24, you might have seen something like that, or 100, whatever it may be. So you might have been on, let's say your host is on .100 at the end, and this host is .200, right? It's still the same network because the prefix of 192.168.0.xxx is still the same network segment. And so the switch will actually just say, hey, rather than go outside of this network, let's keep it inside the network, keep it in the house, keep my secrets inside. That's what it means. It's just really a way of separating domain and broadcast segmentation at the single network layer. So when you think of technologies that are associated with this, MAC addresses, network switches, VLANs. And a VLAN, as you'll see later on in your lab, it's just another way of saying, hey, instead of my switch being one large switch, how about we just segment it into 2 switches and make it act like it's 2 different networks on 2 different IP address ranges. Not what I want to do, but hey, if you wanted to do that, depends on what it is. Now, VLANs are actually a great way for geographic needs to traverse over multiple buildings. So, let's say, for instance, this needs to be VLAN 1 on port 1, and this needs to be on VLAN, uh, we'll just VLAN 1, VLAN 2, right? And let's say that VLANs, let's change this up. Let's have this 1 and 1, and these two can stay together, it doesn't matter, but these two are on two different buildings. Let's say device A and device D on two different buildings. Having them on VLAN 1 makes them on the same logical network segment versus B and C, so they don't have to have wired connections anymore. They can actually say, hey, I'm local, I don't have to go traverse the internet. So rather than adding more resources to my frames and creating packets with using a router, let's just say, hey, logically, I can traverse to a different building over multiple layer 1 and layer 2 mediums without having that overhead of a layer 3 route. So that's what VLANs are really for. We'll get more into that into the labs. You'll see more and more of these as you go on into your career. Now, layer 3 devices, we talked about routers. Right? After we get to a binary bits of ones and zeros, you have a frame. And then you have routers. Routers are what we forward stuff from one network to the other. Notice that each of these networks are different. So this is a 10/10,000/8, right? And everything has a different IP address, but we want to send something to 12.0.0.0. Well, it's not on the same network segment, right? It's not on the same switch anymore, layer 2. So now we have to forward the information, hence that you see this little pi here. Routers always denoted by pi. Pi is really awesome. But remember that layer 3 basically says, hey, I'm not on your local network anymore. I have to go somewhere else. And we have things like, just like what GPS is, where we have, or maps, old school maps, where things were, what a route stuff. That's what a router does. They all have tables together of mappings of each other over and over across different networks. The longer you get away from your network to the other side of the world for sending a piece of data, the longer it's going to take. And the more routes it might have to take and more different transactions it has to go through different routers for. In this case, we might have to traverse 3 different routes to get from point A to point B, depending on what the routing table efficiency is. You would never want a packet to go through here and then from here to here. No, that's just daisy chaining. It doesn't make a lot of sense. You really want an efficient route from going, hey, I know where this is. I'm going to go from 14 here and make that stop directly. Now, because these are intermediary networks and they're only connected by, not connected directly, but they're connected directly by that middle router, that's what we call TTLs, and time to lives, where we say an IP TTL, right? You starting from your local route to another hop and then another hop. So you have to have 2 hops to get to your final destination if you were sending it to those 2 groups of devices. Again, these are based on IP addresses. So IPv4 uses octets of 8. IPv6 is a 128-bit address. So the equivalent of having 3 IPs for every cubic square inch on the planet. It's pretty crazy. So that's what we mean by layer 3 devices. Think of addresses. Think of addresses to your house. From one house to another, what's my route to get to your house? If Dennis would come to your house today, what's your GPS coordinates and what's the route to take there? Take I-95. Who knows? That's what routers do, layer 3 routes. Now, I say devices in combination of what layer 4 to 7 looks like. That's because really we think about it at a higher abstraction. So not only are we saying, hey, get to another city, Dennis is going to come visit you, and rent a car, that's my route path to you. I don't know what garage to park next to you at. I don't know the data that is being sent. I might have the data with me, but I wouldn't know about it at a route layer, right? Your GPS doesn't understand. Me, let's say you and I are both applications. We understand what kind of data is being traversed. And so devices that operate at higher layers understand layers at different content and payload perspectives in the encapsulation movement. So remember, packets are always made at layer 3 and above. Frames are layer 2 and below, or actually layer 2 only. So let's review our concept real quickly. Layer 4, we operate on ports. So if I have a firewall, I understand TCP, UDP, source and destination ports, and the IP address to and from. So I can make blocking decisions based on it or allow decisions based on that. At layers 5 through 7, right, I have encoding information, I have data, I have payload. I understand the content of my nature of what is being sent. So maybe Dennis was not sending you a great package for a gift. Maybe he's sending you something malicious. This is an example of a content match at 5 through 7, understanding a payload, right? Understanding what I'm actually sending you. I'm inspecting what's in Dennis's gift being sent to you. Is it a true gift? Well, the gift of ABCD may not be the gift to you. So that's at layers 5 through 7, understanding content. Remember that layers 3 and 4, which are basically most firewalls today, that's all ports and IP addresses. So it's important to keep that distinction in mind, but the higher you go, the smarter your devices are. That's it for this module. Hope you had a great time. We'll see you in the next module.